Welcome back, AP Statistics. This is part 2 of chapter 20. We're going to be talking about type 1 and type 2 error to start this lesson. So type 1 error, we call this a false positive. That is when the null hypothesis is true. The null hypothesis is what we should not reject, but we make the mistake of rejecting it. So that is called type 1 error. Type 2 error we call a false negative, and that is when the null hypothesis is in fact false, but we fail to reject it. I find that a visual representation of these types of error is helpful, so here's one that I hope works for you. With type 1 error, we should not reject the null hypothesis, but we do. And in type 2 error, we should reject the null hypothesis, but we don't. So there you go. Hope that helps you. The go-to example for the concepts of types of error is this example right here. We're going to let H sub 0 be not pregnant and H sub A be pregnant. All right? We're assuming that someone is not pregnant until there is clear evidence that they are. Type 1 error, the false positive, is that the null hypothesis is true, but we reject it. So in this example, it would be this man on the left here is clearly not pregnant. The null hypothesis is true, but the doctor, for whatever reason, says he is. So we reject the null hypothesis and conclude pregnancy, obviously erroneously. Type 2 error, that is the false negative, is that the null hypothesis is false, but we fail to reject it. So the woman over here is clearly pregnant, all right? That is obvious. But the doctor says she isn't. We fail to reject. So there is the pregnancy example. You've seen a Pokemon example and a pregnancy example. Hope that helps. So here are the possibilities for a hypothesis test. You have two components here. You have what is actually going on and the decision that you make. If, perchance, you were to reject the null hypothesis and the null hypothesis is in fact false, that is an okay and quite interesting result, all right? Things are not as we supposed in the null hypothesis. However, if we fail to reject the null hypothesis and the null hypothesis turns out to be true, that's okay, and I mean, it's what we expected in our hypotheses. That's what, for the examples we've done so far, P sub 0 said anyway. So it's an okay result, it's an appropriate result, it's the correct result, and it is also boring, unlike this one. However, there are two types of error. If we reject a true null hypothesis, that is type 1 error. That is the false positive, all right? We were accusing the null hypothesis of being untrue when in fact it was. On the other hand, we have type 2 error, which is the failure to reject null hypothesis when the null hypothesis should have been rejected. That is the false negative. One way of remembering which error means what, and this is very easy to forget, so we're going over this many times. Type 1 error means the first hypothesis is right, asterisk, we'll talk about that, and we reject it. Type 2, the second hypothesis is right, but we don't support it, okay? So we don't reject the null hypothesis and support it. All right, and that little asterisk next to the quote, right, is you cannot prove a null hypothesis is right. You can never support a null hypothesis. We talked about that with the example with the swans, the finding all white swans versus a swan of some other color. So we cannot prove a null hypothesis is right, only that there is not enough evidence to prove it wrong, but just go with it here. This picture from our book, which I'm sure has been in other books as well, is quite helpful, and I would encourage you to put it to memory. So let's do a real life kind of example when we need to talk about types of error. Suppose a study were conducted about the effectiveness of a heart medication. The researchers want to know if the medication lowers the risk of heart attack for patients with heart disease. However, with all medications, there are side effects. So there are two scenarios to consider. If the more costly error would be to deny people possibly effective treatment, which type of error would we want to avoid more? Which would be the more costly error, type 1 or type 2? And number 2, if the more costly error would be to produce a medication that is effective but would be obsolete because it has more side effects than the competition, which type of error would we want to avoid more? Take a minute, consider these two intriguing problems, see if you can come up with an answer, and then compare your answer to mine. Okay, I'll assume we're ready to continue. Let's look at these answers. For number 1, I'm more concerned with type 2 error. The alternative hypothesis is worth supporting, but we failed to reject the null hypothesis. Why? Well, if the medication shows signs it's effective, and we are concerned with denying people possibly effective treatment, if that's the biggest concern on our minds, failing to reject the null hypothesis and support the production of this drug may keep ineffective treatment out of patients' hands. Now, as you probably guessed, the answer to number 2 is going to be type 1, all right? And the answer may be a little more nuanced here. So for number 2, our biggest concern is, well, there are already other drugs on the market. We don't want to produce this medication, we don't want to manufacture this drug that has lots of side effects unless there's a really clear result. Otherwise, we would run the risk of losing a lot of money because no one's going to want it. That guy on the commercial is going to be speed talking for way too long, and people are going to be concerned for their lives about this drug. So, type 1 error is the one that I'm concerned about the most, and that is when the null hypothesis should not be rejected, but we do. All right, so even if the medication shows signs it's effective, rejecting the null hypothesis may incline the manufacturer to make a medication that's not going to sell because of the multitude of possible side effects. If there are a lot of side effects, we want a really clear result from the medication or it's not worth it. If we know that there are going to be side effects, if we know that there are clear risks, we need to make sure that the reward is salient or it's not worth producing this drug. So we see in problem 1 and 2, depending on what we want to avoid, that's going to shape how we design our hypothesis test. So now we get to link the types of error, specifically type 1 error, with things that we have discussed before. Recall that alpha is the likelihood of sampling data that would be considered significantly different than what we expect, assuming the null hypothesis were true. If our p-value is less than alpha, that is the statistics definition of a significant result. Thus, we can say that alpha is the probability of having type 1 error. That is one way to look at it. If the null hypothesis should not be rejected, alpha would be the probability that we reject it. Would that not be the case? So we would say the probability of choosing the alternative hypothesis, given the null hypothesis is true, is alpha. The probability of committing type 2 error is a little more esoteric, all right? It's a letter that we have not seen before. We'll see it later in a different context, but it is a letter that we haven't really seen much before, and that is failing to reject a false null hypothesis. That is called beta. All right, so the probability of committing type 1 error is alpha. We've seen alpha before. It's our level of significance. Beta is the probability of committing type 2 error. That's the odds that we fail to reject a false null hypothesis. And what's interesting about beta and what makes it a bit unique is that though we can control alpha by adjusting the level of significance, we cannot manually adjust beta. We can make alpha any percent we like, usually 10% or below, but we cannot manually adjust beta. But there is something else we'll learn about in this section that is directly related to beta that we can use to calculate beta. And right on cue, we have to talk about the power of a hypothesis test. The power of a hypothesis test is the probability of rejecting a null hypothesis that is actually false. If a null hypothesis is false, you want to reject it. And the odds that you do is called the power. Since we want to reject a null hypothesis if it's false, we want the power to be high. Okay? You can think of power like the strength of a lie detector for the null hypothesis. How capable are we of picking up on a lie in our null hypothesis? In prior examples, how likely are we to pick up on a lie for our p sub 0 value? Okay? Since the power is the probability of rejecting a null hypothesis when we should, and beta is the probability of not rejecting the null hypothesis when we should, there is a relationship we can find. The power is the complement of beta, and of course, vice versa, all right? Power is the odds we reject a null hypothesis when we should, and beta, the odds of type 2 error, is the probability of not rejecting a null hypothesis when we should. Remember type 2 error, the alternative hypothesis is legit, but we don't reject that null hypothesis. That means power and beta are complements, all right? And that is how we compute beta. We understand power, and that's also how we understand power. We have a value for beta to work with. Now we need to talk about power and effect size, okay? So suppose we're doing a study on the proportion of students who forget something to class on a given day. We've all been there. We've all been part of that assumed p sub 0 equals 6%, all right? Scenario 1. The true proportion of students who forget something to class is about 7%. We are off, but not by much, okay? 7%, it depends on the sample size, depends on some things, but that's probably not a significant result. However, scenario 2. Students are more forgetful than we thought. The true proportion of students who forget something is 22%. That is very far off from 6% last I checked. That is almost certainly a significant result unless our sample size is atrociously small. In which of these scenarios does the test have more power, that is, ability to detect an errant null hypothesis? In other words, in which scenario would it be more likely that our sample would yield a significant result? Well, you just look at the numbers, it's scenario 2, all right? And notice the distance between 7% and 6% in scenario 1 and 22% and 6% in scenario 2. You should be thinking of the term effect size. The effect size, the distance between p sub 0, the assumed proportion, and p, the true proportion, is greater in scenario 2, all right? If we were to construct a confidence interval for scenario 2, it would be centered, if you recall, at 22%, okay? If this were our sample proportion, if we took a good sample and this were our sample proportion, the confidence interval would be centered at 22%. That means the effect size is somewhere in the ballpark of 16%, give or take. That's a big difference compared to an effect size that would be significantly smaller. Guess I didn't need to say that. The bigger the effect size we find, the greater the power of the test to detect an errant null hypothesis. So let's keep talking about the power of a hypothesis test. How can we increase power? Power is something that we want for a hypothesis test. We can increase the power of a hypothesis test by making alpha greater. If you make alpha greater, it's easier to get in that level of significance. It's easier to get a p-value that is below a high value for alpha, all right? It's easier to get in an alpha of 10% than an alpha of 5%, and easier to get within an alpha of 5% than an alpha of 1%, so on and so forth, all right? So the null hypothesis is easier to reject if alpha is greater. It does, though, increase our risk of type 1 error, though. Type 1 error, null hypothesis should not be rejected, but we do, all right? And that is a risk that we take when we make alpha greater, all right? We increase power by making alpha greater, but that does open us up to type 1 error, okay? So we see in the graph on the left, we have a high value for alpha. That's a lot of area right there on the right-hand side. That is a high power, low risk of type 2 error, but high risk of type 1 error kind of situation. If our area on this right tail specifically that we're looking at is quite big, we have high power. It's easy to get a p-value that is less than this area, okay? But we do run the risk of type 1 error. If the null hypothesis is in fact true, it's easy to reject it because the area is so big. However, if I make alpha low, there is low power. This p-value needs to be quite low to get within this area, to be this area big or lower. However, there is also a low risk of type 1 error. Since our p-value has to be very small to be less than that area, our odds of committing type 1 error go down. So there's a little bit of a catch-22 going on, and that happens a lot in statistics, catch-22s. But there is one way of fixing everything, and it is the silver bullet of statistics that we have seen before. And we'll get to that. But first, we got to talk about whatever this dog is doing here. We'll get to the dog in just a moment. We can increase the power of a hypothesis test by doing other things too. Decreasing unexplained variability. All right, so the more unexplained variability we have, the less power that we have. The more chaotic things are, the less obvious a result is. Should be clear enough. So we decrease unexplained variability by doing several things. We could use stratified sampling, which, if you recall, that divides the population into strata with similar characteristics. In other words, we could, if we're doing a study on a school, divide the school up into grades and sampling from each grade. All right, so there we go. We would divide the population into strata with similar characteristics and then sample proportionally to the representation of those strata within the population. Okay, that would limit unexplained variability. That's a technique we learned way back in the day. We could use a blocked experimental design. So if we're performing an experiment, we could divide the experimental groups into blocks with similar characteristics. For example, we could divide the subjects in the control and treatment groups between boys and girls, since the sex of the person may affect the results. And so we could use blocking in an experiment. If we think there's a variable that may affect the results in some meaningful way, we don't want the control group to have all of the boys and the treatment group to have all of the girls. That result should be thrown in the trash where it belongs. Blocked experimental design decreases unexplained variability, makes results more clear, increases power. We like that. Also, and this is one that comes with consequences, which we will see later on in this lesson, narrow the scope of possible subjects in the population. In other words, instead of conducting a study on all Canis familiaris, all breeds of dogs, and dogs come in all shapes and sizes, maybe we just conduct a study on toy poodles. Now, what is the potential pitfall of that? Well, then our results can only apply to toy poodles, all right? It would be kind of ludicrous to apply those results to pit bulls or Great Danes or golden retrievers or even other toy dogs like pugs, all right? These are dogs come in all different shapes and sizes, and it would be unwise for us to expand our results to apply to all dogs. We would just be applying them to toy poodles. What it does do, though, is it limits unexplained variability and makes our results more clear, especially when studying a population as diverse as the world of dog. However, here comes the silver bullet. You increase the sample size. Some of you may have seen this coming. You increase the sample size. That decreases the odds of both types of error. So if you want to increase power, you increase the sample size. Something we've seen all throughout statistics, that the bigger the group, as long as it's sampled well, the more easy it is to understand. Individuals are wildly chaotic, but groups are predictable. All right? So you increase the sample size, increase the size of the group. As long as you're sampling well, you will decrease the odds of both types of error and increase power. That is the best. So let's put everything together. As power, that is the ability to reject a false null hypothesis, increases, the risk of committing type 1 error, that is rejecting a true null hypothesis, also increases. All right? So as power increases, the risk of committing type 1 error increases. If we want to reject that null hypothesis, we could get too eager and commit type 1 error. That's what's going on. And the risk of committing type 2 error decreases. Remember, the odds of type 2 error and power are they are complements of each other. All right, so as one increases, the other decreases. Simple enough. And there you go. Power equals 1 minus beta. As power increases, the probability of type 2 error, that is beta, decreases. But we want the best of both worlds, just like Hannah Montana. Increasing the sample size protects against both kinds of error. Likewise, small sample sizes leave us vulnerable to both kinds of errors, and my reference has left you vulnerable to having this song in your head for the rest of the lesson. And you know what? Sometimes that's how it works. Think of the formula for the standard deviation for the sampling distribution for sample proportions or means. And yes, we're going back for that one. If we have a large sample, that means that n, which is in a denominator, is going to make the standard deviation or standard error small, okay? But if we have a small sample, that's going to make a standard deviation or standard error large, because again, n is in a denominator, all right? So the bigger the value of n, the lower the variation. And that's what I just said. The smaller the standard deviation, the less the sampling variability, the clearer our result. And the less the sampling variability, the more power, and we like power. If there's a false null hypothesis, we would like to be able to reject it. The only downside of increasing sample size is money, money, money. And that is the one thing you don't have to worry about as an AP Stat student. But in the real world, as Paramore once said, ain't it fun living in the real world when you have to worry about the cost of big samples. So that'll take us to our last set of problems. Suppose a large fast food chain develops a new look to its menu. Good for them. Hoping that it will encourage more customers to order the combo meals. Before switching to the menu in all of its thousands of restaurants, it first decides to try it out in a random sample of restaurants and compare combo meal sales among them with combo meal sales among a randomly selected control group of restaurants. We're going to define P sub T, T is for treatment, to be the proportion across all of the restaurants of customers who would order a combo meal when presented with the new menu. And that's what we want them to do. We want that combo menu and a combo meal from the menu. And define P sub C, C is for control, to be the proportion across all of the restaurants of customers who would order a combo meal when presented with the old menu. The hypotheses of the fast food chain would be H sub 0, no difference there. New menu might look cool, but not encourage us to buy combo platters. Versus alternative hypothesis, the treatment group, the new menu, folks using the new menu are more likely to order the combo platters than people with the old control menu. All right, so those are our two hypotheses. Let's look at number 4. Describe an advantage to the fast food chain of using a significance level of 0.05 compared to a significance level of 0.01, and also describe a disadvantage. Take a moment, pause the video, try this one on your own and see what you get. All right, I'll assume we're ready to continue. Using a higher significance level increases the power, okay? If we make alpha bigger, we're more likely to reject the null hypothesis, but it does raise our risk of type 1 error. If the null hypothesis is in fact reasonable, if we should not reject it, but we do, that is type 1 error. So there are risks involved. Number 5. Describe an advantage to the fast food chain including 200 of its restaurants in the study compared to including only 50 restaurants, and then describe a disadvantage. And by the way, you may be wondering why this problem starts with number 4. I decided not to do numbers 1 through 3 earlier in the section, so we're starting with number 4 because that's how we roll. Okay, so describe an advantage and a disadvantage, right? Give this one a go, pause the video, unpause when you want to see the answer. Okay, I'll assume we're ready to continue. Here we go. Using a larger sample size decreases the risk of both types of error and also increases power, all right? Because if we decrease the odds of type 2 error, that means we increase power because they are complements. But will take more effort and will almost certainly be more expensive. So it's more effort on our part, more money on our part. So there is a disadvantage to increasing the sample size, but nothing you need to be concerned with in AP Stat. The money is no issue for us, but in the real world, just as Paramore says, ain't it fun? Number 6, describe an advantage to the fast food chain of including in its study only restaurants located in large cities, and describe a disadvantage. Think about the slide with the poodle on it and see if you have an answer to this one. Pause the video and try this one, and then you can check the answer after you're done. Okay, let's see it. Narrowing the scope of possible subjects, like narrowing the study of all dogs to the study of just toy poodles, limits unexplained variability, which increases the power of the hypothesis test. Less unexplained variability, more power for the hypothesis test, but also limits how applicable our results are. Okay, so if we're just talking about large cities, it would be irresponsible for us to apply them to suburbs, towns, or the countryside. All right, so if we know a bit about large cities, we can't apply that broadly. All right, but we do get a more clear, cut and dry result, or at least we should. And what you should do is give your best on this homework. There's a lot of terminology, a lot of concepts here: type 1 error, type 2 error, alpha, beta, power, all that other stuff, level of significance, hypotheses, null hypothesis, alternative hypothesis. This homework will help you put it all together if you've taken some good notes and reflected on these videos. And sorry if you still have that Hannah Montana song in your head. I'm not sorry. Have a good day.